Assalamualaikum warahmatullahi wabarakatuh. Hello everyone, my name is Hani-N. I'm from the Physics Study Program. I'm from class N. In this video, a segment I will read about the chapter on symbols and equation in physics. Constant acceleration, a special case. In many types of motion, the acceleration is either constant or approximately so. For example, you might accelerate a car at an approximately constant rate when a traffic light turns from the red to green. Then graphs of your position, velocity, and acceleration would resemble those in Fig 2 until 9. Note that A in parentheses T in Fig 2 until 9C is constant, which requires that V in parentheses T in Fig 2 until 9P have a constant slope. Later, when you brake the car to a stop, the acceleration or deceleration in common language might also be approximately constant. Such cases are so common that a special set of equations has been derived for dealing with them. One approach to the derivation of this equation is given in this section. A second approach is given in the next section. Throughout both section and later when you work on the homework problems. Keep in mind that these equations are valid only for constant acceleration, or situation in which you can approximate the acceleration as being constant. First basic equation, when the acceleration is constant, the average acceleration in instantaneous acceleration are equal, and we can write e key 2 until 7 with some change in notation as a equals avg equals v minus v0 divided t minus 0. Here, v0 is the velocity at time t equals 0, and v is the velocity at any later time t. We can recast this equation as v equals v0 plus at. As a check, note that this equation reduces to v equals v0 for t equals 0 at its mass. As a further check, take the derivative of e2 until 11. Doing so yields dv divided dt equals a, which is the definition of a. Figure 2 until 9p shows a plot of e2 until 11. The v in parentheses t function, the function is linear and thus the plot is a straight line. Second basic equation, in a similar manner, we can rewrite e2 until 2 with a few changes in notation as v avg equals x minus x0 divided t minus 0. And thus as x equals x0 plus v avg t, in which x0 is the position of the particle at t equals 0, and v avg is the average velocity between t equals 0 and a later time t. For the linear velocity function in e2 until 11, the average velocity over any time interval, say from t equals 0 to a later time t, is the average of the velocity at the beginning of the interval in parentheses equals v0, and the velocity at the end of the interval in parentheses equal v for the interval from t for the interval from t equals 0 to the later time t, then the average velocity is v avg equals half in parentheses v0 plus v. Substituting the right side of EQ2 until 11 for v yields after a little rearrangement. V AVG equals V0 plus half AT. Finally, substituting EQ2 until 14 into EQ2 until 12 yields x minus x0 equals V0 t plus half AT square. As a check, note that putting t equals 0 yields x equals x0 as it must. As a further check, taking the derivative of EQ2 until 15 yields EQ2 until 11, again as it must. Figure 2 until 9a shows a plot of EQ2 until 15. The function is quadratic and thus the plot is curved. 3 other equation 2 until 11 and 2 until 15 are the basic equation for constant. 3 other equation 2 until 11 and 2 until 15 are the basic equation for constant acceleration. They can be asked to solve any constant acceleration problem in this book. However, we can derive other equations that might prove useful in certain specific situations. First, note that as many as 5 quantities can possible be involved in any problem about constant acceleration, namely x minus x0, v, t, a, and v0. Usually, one of these quantities is not involved in the problem, either as a given or as an unknown. We are then present with 3 of the remaining quantities and asked to find the fourth. Equation 2 until 11 and 2 until 15 each contain 4 of these quantities but not the same 4. In EQ 2 until 11, the missing ingredients is the displacement x minus x0. In EQ 2 until 15, it is the velocity v. Thus, two equations can also be combined in 3 ways to yield 3 additional equations, each of which involves a different missing variable. First, we can eliminate t to obtain v square equals v0 square plus 2a in parentheses x minus x0. This equation is useful if we do not know t and are not required to find it. Second, we can eliminate the acceleration a between EQ2 until 11 and 2 until 15 to produce an equation in which does not appear. X minus x0 equals half in parentheses v0 plus vt. Finally, we can eliminate v0 obtaining x minus x0 equals vt minus half at squared. Note the subtle difference between this equation and EQ2 until 15. One involves the initial velocity v0, the other involves the velocity v at time t. Table 2.1 Equation for motion with constant acceleration. Equation number 2 until 11, equation v equals v0 plus at, missing quantity x minus x0. Equation number 2 until 15, equation x minus x0 equals v0 t plus half a t squared using quantity v. Equation number 2 until 16, equation v squared equals v0 squared plus 2a in parentheses x minus x0 missing quantity t. Equation number 2 until 17, equation x minus x0 equals half in parentheses v0 plus v t missing quantity a. Equation number 2 until 18, equation x minus x0 equals vt minus half a t quadrat. Half a t squared. Missing quantity v0. Table 2.1 lists the basic constant acceleration equation e 2 until 11 and 2 until 15, as well as the specialist equation that we have derived. To solve a simple constant acceleration problem, you can usually ask an equation from this list. If you have the list with you, choose an equation for which the only unknown variable is the variable requested in the problem. A simple plan is to remember only EQ2 until 11 and 2 until 15 and then solve them as simultaneous equation whenever needed. Thank you. Wassalamualaikum warahmatullahi wabarakatuh.